Okay, in this video I am going to show you the mathematical derivation for the velocity as a function of time for the linear form of air resistance in the vertical direction. So we're using the linear form of air resistance in 1D, and we're talking about the vertical direction. And remember, we're using the convention that positive y is in the down direction. All right. And so to remind you, we used this substitution that we're letting u equal to v minus v terminal. And remember that that means that du dt equals dv dt. And so our differential equation that we wrote down from applying Newton's second law to the situation can be rewritten in terms of u as du dt equals minus b over mu. Right? And so then we're going to use our separation of variables trick to get things on the same side, same variables. Right? So I have du over u. And so now I can integrate that. And we know that over here we're going to get the log of u. And over here we're going to get minus bmt plus some constant. And then I exponentiate, and I should say, I should have pointed this out, right? That the point of all this is that having used that u substitution, we now have an equation that looks just like the equation we used to solve the horizontal direction case, right? So really, from here on out, we're using exactly the same steps as we did earlier. So we should start to recognize them, right? So we undo the log by exponentiating everything over here. So we're going to get like this, e to the c, e to the minus b over mt. And I'm just going to call this a new constant. I'll just call it a for the moment. And let's see. So let's go ahead and now we can undo this substitution we did for the u variable, right? Because we really want to know about v, not u. So I'll go ahead and undo that. U of t is equal to v of t minus the terminal velocity, right, is a e to the minus b over mt. And now I can find a by setting t equals 0. Right? I'm going to put t equals 0 into this expression and get v of 0 minus v terminal equals this constant, right? Because t0 in the exponential just works out to 1. So that's what that a value is. And so I can put that into this upper equation up here to say that v time minus v terminal equals v naught minus v terminal times this exponential term. Oh. Okay. So let's actually make a new page and write that so we can see it clearly. Come on. Right, so again, what we have is vt minus v terminal equals v naught minus v terminal quantity times the e to the minus b over mt. Okay, so now let's clean this up a little bit. We'll put the v of t on one side. So it's v naught minus v terminal e to the minus b over mt plus v terminal. Right? And now I'm going to, so you could leave it like that, but to help us to better understand what this means, what's going on, I'm going to separate it out so that I have one term with v naught and the other term with v terminal. So I'm going to put v naught over here. And then what do I have over here? I have a v terminal all by itself and v terminal times this exponential. So I can pull the v terminal out. 1 minus e to the minus b over mt. Yeah. So this is something you've seen before, right? We just got done playing around with this 1 minus a decaying exponential kind of term. So you have a sense for what the graph of that looks like. And this is just a decaying exponential, so you have a sense of what that graph looks like. So you can use your knowledge of what these graphs look like to try to predict graphs, right? So you could now go and sketch what would a graph of v of t versus t look like. And so we might try a variety of cases. We might start out by saying, what if I make v not 0? So have it start from rest. Then, of course, this term will just go away, and you'll just have this kind of term. And we could try then a different values of v naught, different small value, big value, that kind of stuff, and see how that would affect it. That's actually the question in here, right? So now that we have this expression for our terminal velocity, the next thing is to sketch a graph of v of t if there's 0 initial velocity, and then try sketching graphs if the initial velocity is down, smaller than v terminal, or down, greater than v terminal. All right, so I'm going to ask you to do that and bring your solutions to class.